Welcome to Session 8. Until now, every system we've solved had at least one straight line in it. That line was our friend. It was the easy equation, the one we substituted with and back substituted into. Today, the line is gone. Both equations are curved. And I want to start by breaking an assumption you may not know you have. You probably believe a system has at most two solutions. That was true for a line and a parabola, because substitution gave us a quadratic. It is not true in general. Today you'll meet a system with four. Here's the first big idea. When both equations are nonlinear, don't reach for substitution automatically. Look for cancellation first. Take x squared plus y squared equals 13, and x squared minus y squared equals 5. Look at those. Same terms, opposite signs on the y squared. Add the two equations together, and the y squared vanishes. 2x squared equals 18, so x squared equals 9, and x equals plus or minus 3. Now subtract the second from the first, and this time the x squared vanishes. 2y squared equals 8, so y squared equals 4, and y equals plus or minus 2. That's it. No substitution, no expanding, no quadratic formula. Just addition and subtraction. This is elimination, the same move you learned for linear systems, and it works beautifully on nonlinear equations, as long as the terms line up. Now count the solutions, carefully, because this is the part that surprises people. We found x equals plus or minus 3 and y equals plus or minus 2. So how many ordered pairs is that? It's not 2. Each choice of x can pair with each choice of y. 3 and 2, 3 and negative 2, negative 3 and 2, negative 3 and negative 2. That's 4 ordered pairs. And here's why all 4 genuinely work. Look back at the original equations. Both of them contain only x squared and y squared. Squares destroy sign information. So the system literally cannot tell 3 from negative 3. Flipping any sign leaves both equations unchanged. Geometrically, these two curves are a circle and a hyperbola, and they cross at 4 points, one in each quadrant, arranged in perfect mirror symmetry. Not every system is that symmetric, so here's the second big idea. Treat a repeated expression as a single unit. Take x squared plus y squared equals 25, and x squared minus y equals 19. Notice these don't line up for elimination. One has y squared, the other has a plain y. But look at what repeats. X squared appears in both. So solve the second equation for that whole unit. X squared equals 19 plus y. Now substitute the unit, not a variable, the whole expression, into the first equation. 19 plus y squared equals 25. That's y squared plus y minus 6 equals 0, which factors as y plus 3 times y minus 2. So y equals negative 3 or y equals 2. Now go back for x. If y is negative 3, then x squared equals 16, so x is plus or minus 4. If y is 2, then x squared equals 21, so x is plus or minus the square root of 21. 4 solutions again, 2 y values, each carrying a plus or minus x. Now, a family of questions the SAT loves, built entirely on the identities from Session 4. You're given the sum and the product, or the sum of squares and the product, and asked for a combination. The key identity, x plus y squared equals x squared plus 2xy plus y squared. So if x squared plus y squared equals 25 and xy equals 12, then x plus y squared is 25 plus 2 times 12, which is 25 plus 24, 49. So x plus y is plus or minus 7. 2 answers, because nothing in the problem tells us whether x and y are both positive or both negative. And the twin, x minus y squared, is 25 minus 24, which is 1. So x minus y is plus or minus 1. Notice we never found x or y individually. We didn't need to. The question asked for a combination, and the identity produced the combination directly. Here's the same identity run backwards, which is a lovely trick. Suppose you're told x plus y equals 7, and x squared plus y squared equals 25. Find xy. Square the sum, 7 squared is 49, and that equals x squared plus 2xy plus y squared. But we know x squared plus y squared is 25, so 49 equals 25 plus 2xy. That gives 2xy equals 24, so xy is 12. One identity rearranged 3 different ways answers 3 different question types. That's why I told you to learn these by heart in session 4. Now, the essential caution. Because the 4 solutions idea can be over-applied. Sign flips are free only when every equation depends on squares alone. Watch what breaks it. If one equation is x times y equals 6, then flipping just one sign turns the product negative, and negative 6 is not 6. So only sign pairs that keep the product positive survive. If one equation contains a plain y, like x squared minus y equals 19, then y and negative y are genuinely different. Look back at that system we solved. We got plus or minus 4 for x, but for y, we got exactly negative 3 and exactly 2. No plus or minus. That asymmetry is the plain y doing its work. So the rule is, generate candidates from the structure, then test each one against every original equation. The structure tells you where to look. Verification tells you what's real. Let's do one from your practice set. If x squared plus y squared equals 25 and x times y equals 12, what are the possible values of x plus y? Reach for the identity immediately. X plus y squared equals x squared plus 2xy plus y squared. Regroup it as x squared plus y squared plus 2xy. Substitute, that's 25 plus 2 times 12, which is 25 plus 24, which is 49. So x plus y squared equals 49, which means x plus y equals plus or minus 7. The answer is B. And look at choice A, plain positive 7. That's the trap, and it's the popular wrong answer. It's exactly right, except it silently throws away the negative case. Sanity check. X and y could be 3 and 4, giving 7, but they could also be negative 3 and negative 4. Check it. 9 plus 16 is 25, and negative 3 times negative 4 is 12. Both conditions hold, and the sum is negative 7. Let's recap. When both equations are nonlinear, look for cancellation before substitution. Adding or subtracting can kill a whole squared term. Treat a repeated expression like x squared as a single unit and substitute the unit. These systems are not limited to 2 solutions. 4 is common because each squared variable contributes an independent plus or minus. Use the identities x plus y squared equals x squared plus y squared plus 2xy, and the minus twin. Run them forwards or backwards, depending on what you're given. And sign symmetry is free only when every equation is built from squares alone. Strong work on session 8. This is genuinely some of the hardest material on the SAT, and you now have the 2 moves that crack it. Eliminate and treat repeated expressions as units. In session 9, we deal with equations that come with fine print. Radicals and denominators, where some answers are traps planted by the algebra itself.